Hello my esteemed viewers. In this tutorial, the MCQs related to data structures and algorithms are clearly explained. Actually, it comes as a blend of questions pertaining to data structures as well as analysis and design of algorithms. Of course, in this, as usual, in this tutorial, we have chosen the questions of moderate complexity. So as we go down, we will find the first question. We'll just go through. The initial configuration of a queue is A, B, C, D, E. That is A in the front of the queue, and E is at the end. To get the configuration of D, C, B, A, one needs the minimum of, let us see. So D has to come to the front. Therefore, A, B, C should be deleted, or A, B, C should be dequeued. Then D will come to the front. In order to get C, B, and A, we need to have 3 insertions. Therefore, it is 3 deletions followed by 3 insertions. Therefore, this is the correct answer. C is the correct answer. Yeah. The possible number of trees with 3 nodes A, B, C. We will write the possible number of trees, then we will get a clue as to which should be the correct answer. If A were to be the root, then we can have one form of the tree like this, B over here and C over here. Similarly, in the same token, if we want to have C at the root node, then we will have one more tree like this. When we have B at the root node, we will have another tree. And with the A as a node, C can come over here and B can come over here. So that means if A at the root, we can have C at this level, okay, as a child of A, and B as the right child of A. Now, therefore, with A as the root, we will have 2 trees. Therefore, with B, another 2 trees, 2 plus 2 plus 2, that is 6 trees. And this kind of arrangement is also possible. A at the top, then B and C like this. B and C. Now, similarly, if you take A over here once again, it could be C over here and B over here. Therefore, with A as the root, this kind of arrangement is also possible. So with A 2 trees, with B 2 trees, with C 2 trees. So this becomes again 6. So therefore, it is 6 plus 6, 12 trees are possible. Okay, so 12 is the correct answer. Right. Question number 3. The number of swapping needed to sort numbers 8, 12, 7, 9, 31, 19, 5 and 13 in ascending order using bubble sort is. Actually, in bubble sort, it requires exactly in the worst case, it requires, as you know, as you recall your memory, it requires n-1 iterations and n-1 minus I passes. That means in every iteration there will be a reduction of 1 comparison. But anyway, you cannot apply that particular formula and you have to do some kind of a paper and pencil work, and this is the first comparison which is going to happen. But anyway, swapping is not needed because it is already in ascending order. When 22 and 7 is compared, there will be a swapping. 22 will come over here, so number of swapping is 1, and 22 has to go over here, 9 has to come over here, number 2, and when 22 is over here, there is already 31, therefore there is no swapping required. So 3 swappings are happened, and 31, 19, here another swapping should take place. So this is the 4th swapping, and the 5th swapping should also happen, and so also 6 swapping. So after the 6th swapping, 31 will be over here, and it need not be compared in the further cycle. Therefore, if you go on doing some kind of a paper and pencil exercise by literally writing and literally swapping, you will find 14 to be the correct answer. Right. Given 2 sorted list of size M and size N, there are 2 sorted lists of of course 2 sorted arrays, the number of comparisons needed in the worst case by merge sort algorithm is. And I think we can take an example of something like this. Let us say, yeah, we will just put up the answers now. So there is one array with 2 elements, that is m is 2, 3 and 5. Okay, this is sorted. The other array is there, which is 1, 2 and 4. This is also sorted. So this consists of m number of elements, that is 2, and this consists of n number of elements, that is 3. And 3 and 1 is compared, so 1 will go to the sorted array. Okay, once again the probe will move over here, and 3 and 2 will be compared. Okay, 2 will come over here, 3 will remain there only. So the second comparison has happened. Okay, and 3 and 4 will be compared. Okay, 3 will come over here. So 3 comparisons have taken place, and 5 and 4 will be compared. 5 and 4 will be compared, and 4 will come over here, and we will be left with 5. Okay, 5 will be placed somewhere over here. Yeah, after the 4, 5 will be placed. Therefore, by that time 4 comparisons would have taken place. Therefore, it should be m plus n minus 1. If you take any number of elements, and if you do like this, you are going to find the number of comparisons is m plus n minus 1. That will happen only in the worst case. Only in the worst case. If this were to be 1, 2, 3, 4, 5, let us say 1, 2, 3, 4, 5. Okay, this is the best case. 1 and 3 will be compared, 1 will be placed. 2 and 3 will be compared, 2 will be placed in the sorted array. Then whatever that remains will be simply placed over here. So it takes only 2 comparisons. Therefore, the question is under the worst case. So under the worst case, for any number of elements on either side of the array, on both the arrays, and here it is n, and here it is m, and here it is n, it's going to be m plus n minus 1. Yeah, that is the correct answer. Now, the fifth one. A hash table with 10 buckets is something like this, with 1 slot per bucket is shown. Okay, the symbols S1 to S7 are initially entered using a hash function with linear probing. S1 to S7 is placed with initial probing. This is called as hash function with linear probing. Linear probing is also called as closed hashing. Okay, the elements are inserted into the array radially. The maximum number of comparisons needed in searching an item that is not present is. Okay, and let us say you are searching for an element somewhere over here. It will be found. If it is S7, it will be found. There will be only one comparison. If you are trying to find an element which were to be somewhere over here, it would take only 2 comparisons. 1 not compared, 2 not compared, 3 it is not available. Let us say if it is S10. Let us say if you are searching for S4 or an element which will come over here, which will be hashed to this particular block. It is not that one. Let us say the key is K, and K is compared with S6. It is not that one. And once again K is compared with S3. 2 comparisons have happened, and it will be wrapped around and it will come over here. That is the nature of a closed hash table, and it will be compared with S7. That is also not the party. It is not equal to K. This is also not equal to K. By that time 1, 2, 3, 4, 5. Okay, 5th comparison will take place only to find an empty space, and algorithm will stop. Okay, by declaring that the element is not found. Okay, because we are going to search for a key which is not present. Therefore, it would consume the maximum number of comparisons that would happen for a key is 5. Therefore, 5 is the correct answer. Yeah. We'll go for the next question. The depth of a complete binary tree with n nodes. Complete binary tree with n nodes. We will write the picture of a complete binary tree, then answers will be available for us. Okay, and this is a complete binary tree. I will make a sketch of that one. It has complete 2 children. Once again, yeah, 3 nodes have been consumed, and here this is the left child, right child for this fellow, for that parent, and here once again left child and right child. So it consumed 1 2 3 4 5 6 7 nodes, and this is the height of the tree. Height of the tree may be defined as the longest path, okay, that is consumed from root node to a leaf node. So here the longest path is 2, this is 1, this is 2. So height of the tree is 2. So number of nodes are 7. Therefore we will substitute in all the formulas. There is no need to mug up. Okay. So n plus 1 is 7 plus 1 8. Okay. This base is 2. You must remember the base is 2. Therefore it is log 2 of n plus 1. Log 2 of 8 is 3. 3 minus 1 is 2. So this should be the correct answer. And you substitute for, and if you substitute over here it becomes 3. So 3 is not the height. If you substitute over here it becomes still less. Okay, and this is also not the answer. Therefore it should be log n plus 1 minus 1. Okay, for a complete binary tree, of course. Seventh question, which one of the following traversal techniques lists the nodes of a binary search tree in ascending order? So we will just make a sketch of a binary search tree. Of course, binary search tree is an order tree. Let us say this is the node, root node, and an element to the left of this root node should be lesser than this. So there should be 6, and it should be lesser than this. Let it be 5, and it should be greater than this. Let it be 7. And as far as this portion of the tree is concerned, it should be more than that. It should be 10, and it should be less than that. It should be 9. It should be greater than 10. Therefore, let it be 11. Okay. And let us do some kind of an in-order traversal. In-order traversal goes like this: left node, root, and then right node. Left node is 5, root is 6. 5, 6, 7. Right node. Okay, 5, 6, 7. Root node. So okay, left tree is over. 5, 6, 7, 8, 9, 10, 11. Therefore, in-order traversal is to be done in order to arrange the keys of a binary search tree in ascending order. Okay, therefore that is the correct answer. Eighth question goes like this: the average successful search time taken by binary search with 10 elements or 10 keys is. Let us try to find it out. Okay, of course, in order to perform binary search, the keys will be ordered in ascending order, and if you happen to construct a tree of that, it will be binary search tree once again. K5, let us say K5 is the rootal key, and this is K2, let us say. Okay, and we need to arrange like this 10 keys, of course, because the question contains 10 keys, and here it should be K1, that is key 1, and this is K3. Okay, and let us say there is another one, that is K4 to the right. Yeah, K4. And as far as right subtree is concerned, it should be, let us say, bigger than K5, and let us assume that it is K8. Okay, K8, and this becomes K6. Okay, K6 and K9. Why we are arranging like this? Because it will be very easy for us to calculate how many number of comparisons for a particular key. Because in order to find a key in binary search, you should occupy the middle position. Okay, when a of mid equal to key, then key is found. That is a node, that is a code that we just remember, right? Okay, if we are searching for K5, you need only one comparison. If you are searching for K2, 1 and 2 comparisons. Okay, 2 comparisons. And if you are searching for K8, it's once again 2 comparisons. K5 and the K8 is greater than K5, therefore you will just traverse towards right of the tree, therefore you will find K8. By that time you would have done 2 comparisons. So at this level it will be 3 comparisons. Okay, so 1 plus 2 plus 2. Then here 3 comparisons: 1, 2, 3, 4. So 3 plus 3 plus 3 plus 3, that is 4 into 3, that is 12 comparisons. and here at this level it is 3 plus 3 plus 3 plus 3, so it is 9 comparisons. So 12 plus 9 is 21, 21 plus 4 is 25, 25 plus 1 is 26. So it should be 26 divided by 10. Okay, so 1, 2, 3, 4. Of course, this is 4. 4 plus 4 plus 4. This is 12 actually, sorry. So 12 plus 12, 24. 24 plus 4 is 28. 28 plus 1 is 29. 29 divided by 10 keys are there. So therefore 29 divided by 10 is 2.9. So there will be 2.9 average number of comparisons. Okay, right. A hash function f of key equal to key mod 7. Any hash function will be like this only, and we are going to place the value of the key over here, and we are going to do modulo division. That is the method. Okay, this is called as a hash function. With the hash function we will be able to construct a table called as hash table, and this hash table should consist of number of cells equal to 7. Okay, and therefore it will start from 0 and it will end at 6. Okay, so we are going to generate 6 numbers. Okay, 6th cell, actually it is a 7th cell. The number which is being 6 is actually 7th cell because the cell numbering starts from 0. You know all those things. Okay, what is the position of 11? Okay, if you start dividing 37, if you are going to put 37 over here, 37 will have to be placed in, let us say, we will construct a table itself, okay, to avoid any possible confusion. So this is the hash table. Okay, this is the 0th position, and this is 1, 2, 3, 4, 5, 6. 1, 0, 1, 2, 3, 4, 5, 6. Okay, of course you know modulo division will generate starting from 0 to let us say n minus 1. So 7 minus 1, 6. So 6 will be the last number. Okay, we will take out this particular cell. So 37 mod 7. 37 mod 7 is 2. Therefore 37 will come and sit over here. So this is the place for 37. So as far as 38 is concerned, 38 mod 7 is 3. Okay, the remainder is 3. Therefore 38 will come over here. Okay, and as far as 72 is concerned, it will occupy 4th cell, because 72 mod 7 is the remainder is 4. And as far as 48 is concerned, 48 will have to be placed at 6th position. So 48 will come over here. Okay, because 7 6 are 42, what remains is 6. Okay, the 48 will go and occupy over here. As far as 98 is concerned, it is 0, because 98 is divisible by 7. So 98 will come and sit over here. So as far as 11 is concerned, 11 mod 7 is 4. At 4, it's already 72 is occupied. Therefore 11 will occupy the 5th cell. Okay, or the cell numbered 5. Okay, so therefore 5 is the correct answer. Right. The average successful search time in linear search on an array of n elements is, the average successful search time in linear search on an array of size n element is. So average search or average running time is calculated for a average case of the algorithm. Average case, it is neither worst case nor the best case, it is the average case. Therefore key can be present anywhere. So if you do some kind of a mathematics using probability theory, you will find that the number of average number of comparisons in case of linear search for a key, for a successful search, of course key being found in any position, is n plus 1 divided by 2. Okay, this you need to remember. Of course it can be proved. Okay, anyway, it involves probability theory. The running time of an algorithm Tn, where n is the input size, is given by, okay, n is the input size is given by, let us say T of n equal to 8 8t n by 2 plus q times n, where q is a constant, of course, where q is a constant. The order of this algorithm is. So as soon as you see the complexity equation written this way, okay, it should be pointing to recursive relation. Okay, such recursive relations will be drawn out if the algorithm is designed using a technique called as divide and conquer technique. So in order to solve such a recurrence relation, we used to use a theorem. We have to use a theorem called as Master's theorem. So Master's theorem states if this is A, so A is equal to 8, okay, this is B, okay, so what is the part? So it is half. Every piece of the problem is divided into 2 halves. So B equal to 2, and D is the power of n. So here it is 1. So D equal to 1. So based on the relationship between A, B and C, A, B and D, Master's theorem directly drives out the complexity of the algorithm. So if here in this case A is greater than B to the power of D, B to the power of D, okay, in that case the complexity happens to be big theta of okay, n to the power of log B log A to base B, log A to base B. Okay, if A is greater than B to the power of D, this is the readily available formula according to Master's theorem. So it becomes n to the power of log A means log 8, log 8 to base 2 means it is 3. Okay, log 8 to base 2 is 3. So it should be n cube. So before we write the answer, we will see other 2 cases, okay, so that if the question were to be different, you should be able to write. If A is less than B to the power of D, in some other case, if this is the true, if this is the case, then the complexity is directly written as n to the power of D. Okay, it belongs to big theta of n to the power of D. On the other hand, if A equal to B to the power of D, then it falls under big theta of n to the power of D log n. Okay, this is the case. Okay, therefore this particular case falls under this category because A is greater than B to the power of D. And if you go further, this can be explained like this. There are 8 in every iteration. There will be 8 problems which are unsolved, each of size n by 2. Okay, this is the meaning. So as many steps as it takes to solve 8 problems, each of size n by 2, plus in order to amalgamate the solutions, this is the time required. Okay, the other part is how much time it requires to integrate the solutions which are obtained by part, because it is divide and conquer algorithm. Yeah, therefore it should be n cube. Right. An algorithm is made out of 2 modules, M1 and M2. An algorithm consists of 2 modules, M1 and M2. If the order of M1 is f of n and that of M2 is g of n, then the order of the algorithm should be I think you must have guessed, it should be max of f of n and g of n. Because if you are given an algorithm size to be something like this, let us say t of n equal to n cube, okay, plus n log n for a typical example, then when we write the complexity of the algorithm, we will always choose the bigger term. Therefore, if m1 is f of n, m2 is g of n, a function of n of course, then the order of the algorithm is the max of f of n and g of n according to this particular rule. Right. Then the concept of big O is, it's a very interesting concept, my dear friends, because this particular concept is used when you have plethora of algorithms which have been written by different algorithmists to solve the same problem. Then it comes the question of selection. selection of the best algorithm. Then this is a metric. Big O is a metric. There are two other metrics also, big O, big theta, big omega. So the point in question is, the concept of big O is, it indicates that the given algorithm is as slow as the algorithms in set O. Set O consists of algorithms which are as slow as the algorithms written by me. Okay, that is the meaning. It indicates that the given algorithm is as fast as the algorithms in algorithm set O. No, this is not the answer. This is the answer exactly. Let us see if there are any other answers too are in the list. It indicates that the given algorithm has the same growth. No, this pertains to big theta. Big theta. This pertains to big omega. And it provides an upper bound to the given algorithm. This is also correct. Therefore, the answers are A as well as D. Okay, big O always provides an upper case or upper limit for my algorithm or the algorithm written by the algorithmist. The running time Tfn is given by a recursive relation, Tfn minus 1 plus C. And there is a condition also, base case Tf0 equal to 0. The order of this algorithm, let us find out. So if we solve this recurrence relation, then we will get the complexity of the algorithm. That is the thing. And we will do what is called as backward substitution. Okay, Master's theorem is not applicable over here because it is not a algorithm which is driven out of divide and conquer, because there is no division that is seen over here. It is straightforward. So we will go for backward substitution. In the second step, it will become n minus 1 because it has to reach the base case. N minus 2 plus another C will be added, so it will become 2C. In the third step, it will become n minus 3 plus 3C. So if we replace this some kind of a pattern that is emerging by some constant, let us say n minus k plus kc, because in the second step 2 is appearing, in the third step 3 will appear. So there is a pattern that is emerging. We need to replace this pattern by a variable and let this variable be c. Then we will look into this base case. When this function Tf0 becomes this function receives a 0 value, then the output should be 0. It is something like this. If input is 0, then factorial of 0 is equal to 0. It is something like this. So in order to get 0 over here, we have to substitute k equal to n. So if k equal to n, this will vanish because it becomes 0 according to the base case, and here n will remain nc. So T of n will reduce to nc, whose complexity should be n because n is the variable size. So n is the correct answer. Right. 15th question. There are 4 different algorithms, A1, A2, A3 and A4. The order of growth is log n, log of log n. Of course, it is to the base 2, okay, needless to say. And n log n for A3, algorithm 3. And A4 is concerned, it is n by log n. Okay, among them, which is the best algorithm? The best algorithm is the one which will have least running time, okay, or least complexity. So if you take input size equal to 10, log of 10 will be 3.33. Okay, this is log of 3.33, which will be very less, and this is 10 into 3.33, 33.33. Well, this 33.33 should be understood to be maybe a number of comparisons. Okay, there is an algorithm where comparison is involved, and as far as this algorithm is concerned, it takes 10 into log 10, that is 10 into 3.3, 33.3 comparisons it will take, and this will be 10 divided by 3.3. Therefore, log of log n is the algorithm which will boast of a very least time of execution. Therefore, A2 should be the algorithm which should be preferred. Okay, right. Sorting useful because when you arrange the things in order, searching becomes easy, and report generation also becomes very easy, because it will become great deal easier to look at a report which has the entire list arranged in ascending order or descending order. it becomes very easy for us to make a look at that particular list. Therefore, this is also correct answer. Reduces storage capacity. Of course, storage capacity has nothing to do with sorting algorithms. Therefore, responding to queries becomes fast. Okay, if we are asked to find some kind of an explanation for a particular key, okay, and if the position of the key is known for us, or it's very easy for us to find out the position of the key, and we can answer any query pertaining to that particular key. Therefore, A, C, and B are the correct answers. Sorting technique that guarantees the relative positions of the same keys. Okay, even after sorting is, it should be stable algorithm. Okay, let us say there are elements 1, 2, 5, 3. Let us say, and there are two equal elements over here, 2 and 2. So before sorting, this is I, before sorting, this is J. This 2 has I, that is first position, and this 2 has, let us say, third position. I is less than J. After sorting, what happens? 1 is here, 2 is here, this 2 is also here, 3 will come over here, 5 will come over here. This is the same 2. It becomes I dash, and this becomes J dash. And here again, it is 1 and 3. So therefore, if the relative positions of the equal valued elements, okay, in an array before sorting, okay, doesn't change, if the relative positions of the equal valued element doesn't change even after sorting, then such an algorithm is called as, such a sorting algorithm is called as stable sorting algorithm. Okay, some of the of course half a dozen of the algorithms that have been devised for sorting exercise have been stable. To name the few, it is merge sort, bubble sort, insertion sort, okay, and quick sort. Quick sort is not stable, of course. Okay, radix sort, heap sort, all these sorting algorithms stable. Majority of the sorting algorithms are stable. This is a desirable property. Okay, this is a desirable property of a sorting algorithm. So this is called as, okay, that means safeguarding the relative positions of equal valued elements even after sorting. Okay, the order of the algorithm that finds whether a given Boolean function of n variables produces 1 is, of course, there can be two answers for every comparison. Either it could be 1 or it could be 0. Therefore, I think we will have to do 2 to the power of n comparisons, because there are n variables and there are only two possible answers. Either it should be 0 or it should be 1, and we don't know for which particular cycle we are going to get the answer to be equal to 1. Therefore, the complexity of such an algorithm happens to be 2 to the power of n, and 2 to the power of n is exponential complexity. So exponential complexity is that complexity where base is a constant and index is a variable. Yeah. The way the card game player arranges his cards as he picks them up one by one is an example of insertion sort. Exactly. Of course, insertion sort simulates the play of cards. Okay, that way the person who is playing the cards will arrange the card, and he will pick up the card, and he will always arrange in a particular order. Therefore, insertion sort is a simulation of play of cards. Right. Next. 28. The average number of comparisons performed by merge sort algorithm in merging two arrays of size 2. Of course, we have to take an example over here, because average number of comparisons is pretty difficult to find out. But anyway, since the question is very simple because it involves only two elements, let us say this is the first case, A, B, C, D. We want to arrange this. This is also sorted array, this is also sorted array. We have to arrange. A is compared with C, A will go to the sorted array. A is and B is compared with C, B will go to the sorted array, and there will be only two comparisons. C and D will be placed over here, no comparisons. So two comparisons will have happened. And the other example could be, it is ACBD. ACBD, they are also sorted. AC ascending order, BD, A and B will be compared. A comes over here, okay, and C and B will be compared. B will come over here, okay. C will still remain over here only. C and D will be compared. C will come over here into the merged array, and D will be over here. So therefore it has taken three comparisons. On the other hand, the last possible example could be, it is ADBC. Let us say ADBC. Here again we need three comparisons. So in all the three possible cases with two elemental arrays, 2 plus 3 plus 3. So 3 plus 3 is 6, 6 plus 2 is 8. So it should be 8 by 3. 8 by 3 comparisons has to happen. Average number of, okay, 8 by 3. The worst case complexity of quicksort algorithm is, I think it should be n square, of course. And you should remember the worst case complexity, the worst case of an algorithm quicksort is supplying or giving an algorithm a list or an array which is already sorted. So if you give 1, 2, 3, 4 to quicksort algorithm and ask the algorithm to arrange it in ascending order, it will do number of comparisons equal to n square for doing nothing. Okay. Of course, in order to understand this, we have to take a deep dive, and I request my interested viewers to go through a tutorial on divide and conquer strategy, wherein quicksort is elaborately discussed. Okay. Anyway, the worst case complexity of quicksort is n square. The worst case complexity of merge sort is n log n. It should be in our fingertips, of course, n log n. Yeah, right. In a heap, if parent position is k, then the children's positions are, okay. Okay, in a heap, the keys are arranged like this. It will have a parental dominance. If this is the key 50, its child keys should be lesser than that. Okay, let us say this should be 25 and this may be 30. Okay, in the same token, if this were to be parent, its children should be lesser than that. It should be 7 and this can be 8. It's an arbitrary example, of course, and this should be maybe 11 and this may be 12. Now there are 1, 2, 3, 4, 5, 6, 7. There are 7 nodes, and this is a heap, typical heap. Okay, because it follows a particular condition for a heap. Okay, every parent should be, and the largest element will be at the root. Okay, 50 is the largest element. It is at the root, and there are 1, 2, 3, 4, 5, 6. There are 7 elements, and 7 by 2 integer division will be equal to 3. So first 3 elements are parents, 1, 2, 3, and the remaining are children. Okay, the remaining, that is 7 minus 3, 4 are children, right? And the question is, in a heap, if parent position is k, then the children's positions are, okay, let us say this is k, so k equal to 2. Okay, this is 1, 2, 3, okay, something like 4, 5, 6, 7. It's only in heap, it's an arrangement of an array like a tree, that's all. Of course, there will not be a picture like a tree in the algorithm also. It's a conceptualization of an array with a shape like this. And interestingly, the array starts not from 0, it starts from 1. Therefore, if this is the children, if this is the parent whose position is 2, the position of its children is over here. So it is 1, 2, 3, 4 and 5. This is 2. This is 4. This is 5. So you just take any big sized heap, you will find this particular thing very much interesting. Okay, so the children position will be 2k and 2k plus 1. If the position of the parent is 2, then its children will be at 4 and 5. 2k and 2k plus. And then in the same token, if the child position is k, then its parent will be at k by 2. Okay, let us say the child position is 5, its parent will be 5 by 2. 5 by 2 is not 2.5, it is 2 because it is integer division. So this is a wonderful relation that is available in heap. Okay, if a parent's position is at k, then its children will be at 2k and 2k plus 1. If the child's position is at k, its parent will be at k by 2. It's a very important thing that we all of us should remember. It's a very interesting data structure. Of course, selection sort is stable in place, not stable in place, not stable, not in place, stable, not in place. Any sorting algorithm, my dear friends, may show two characteristic features, desirable characteristic features. One is stability, which was explained previously, and it should be in place. That means while sorting, you should not demand extra spaces. Of course, sorting should happen just by shuffling within the array, like bubble sort. Okay. Now selection sort is the question. We will take a typical example to answer this. Okay, let the example be 2, 2, 1. Okay, and in the first cycle this will be assumed to be the smallest, and we are trying to arrange it in the ascending order, and we will assume that this is the smallest, and the comparison will be done within the available keys apart from this to find out the real smallest. Interestingly, this will be found to be the smallest in the first cycle, and it will be swapped. Okay, and 1 will come over here, 2 will be over here only, and this 2 will be thrown to the third place. Okay, and when before sorting, the I position was 0, J position was 1. Okay, I is less than J. When the sorting happens, after sorting, I became 2, okay, J remained to be 1. Okay, I dash became 2 and J dash become 1. Now I dash becomes greater than J dash. Therefore, relative positions of the equal valued elements is never safeguarded. It will never happen in some of the cases of a selection sort, and here is a typical example. Therefore, it is not stable. But anyway, selection sort will happen within the given array. It doesn't demand for extra space like merge sort. Therefore, it is not stable but in place. So B is the correct answer. Right. Tower of Hanai puzzle is of logarithmic complexity, exponential complexity, linear complexity, and factorial complexity. Of course, the complexity of Tower of Hanai problem that you know, of course, Buddhist monks are trying to transfer the 64 discs, golden discs, which are placed in, let us say, in a peg A, and they feel it is always auspicious to move all the pegs, all the discs that are available and arranged in a particular order on A to be transferred to C. That is a puzzle, of course, and if you want to of course really go through in detail, and you can refer my ADA course, okay, which has been which is available in YouTube, okay, that comes in the very first chapter itself. Okay, analyzing recursive algorithms. Of course, it is an example of a recursive algorithm, and it will take around 2n minus 1 number of movements, one disk at a time. Okay, all the available disks that are placed in A should be shifted to C following a particular condition. Okay, if there are 2 disks, it is 2 to the power of 2 minus 1. 3 movements have to happen. If there are 3 disks, it requires 8 minus 1, 7 movements. If it is 4 disks, it is 16 minus 1, 15. Therefore, such a complexity is called as exponential complexity. Okay, so with this we have completed the first module under data structures and algorithms, technical aptitude questions, which are being brought out on YouTube to help our student community to find it easier to crash the selection tests. With this, we will close this session. We will come up with another session. Until then, bye. And if you have liked this video, kindly subscribe to my channel.